Hello everyone, welcome back to the second chapter of the course describing patterns in data. This is part 2 video lecture. In the second part, we will learn a little bit more about describing the distribution of one numerical variable. We'll focus on some graphical tools for this. We'll learn about histograms and about density plots. Then we'll pull back a bit and learn some general terminology for describing the shape of a distribution. We'll also take a look at an imaginary population that we'll use for a lot of examples in this course. And then we'll swing back and look at the third major graphical tool for describing a distribution, and that's box plots. Always remember to check that the necessary packages are loaded before you start your work. You may have noticed if you're working on the server version that they tend to stay loaded whenever you're signed in. Even when you sign out and come back again, they'll tend to stay loaded, but it's good to check. So, back to one numerical variable, the graphical tools. Our first graphical tool is a histogram, and there are several types of histograms depending on what you want to see along the y-axis. What you're looking at right now is a frequency histogram of the fastest speed driven for the students in the Math 111 survey. Now, the histogram is useful for one continuous variable, and it divides the x-axis into a number of what we call bins. And in this case, the divisions come every 20 miles. This is 60 miles an hour. Here's 80 miles an hour. Here's 100, 120, 140, 160, 180, and 200 miles per hour. So each of these bins is 20 miles per hour long, you might say. Now the height of each bin is determined by how many students drove a speed that was between the two boundaries of the bin. So what we learn from this first rectangle is that 5 students drove between 60 and 80 miles per hour. The 60 is included in that number, but if someone were to drive 80 miles per hour, that would actually be included in the next rectangle over. So you can see as well that about 30 people drove between 80 and 100 miles an hour. And it looks like maybe just one person drove between 190 and 200 miles per hour. Notice how a histogram looks on the x-axis. It's labeled with the name of the variable and the units. The y-axis simply specifies a count, and notice the title. You can also make relative frequency histograms, and then on the vertical axis what you get is the percentage of the total number of people that are within each bin category. So 30 people drove between 80 and 100 miles per hour. 30 divided by the 71 total people in the study turns out to be a little over 40%, about 42%. And notice the height going up to, yes, looks like about 42%. On the other hand, it looks like you're looking at 60 to 80 miles per hour. It looks like maybe about 7% drove within that range. The final form of a histogram is a density histogram. And this seems rather complicated. At first glance, unnecessarily complicated, but we'll see the great use of these things very soon. Now, in a density histogram, the heights of the rectangles don't tell you anything directly. Rather, it's the areas of the rectangles that are important. The area of each rectangle gives the proportion of the data values that lie in its range. Since 100% of the data values lie somewhere here, then the total area is 1, the proportion that corresponds to 100%. Now let's take a closer look at how this type of histogram works. So remember that rectangle from 60 to 80 miles per hour that had the 30 people in it, 42% of everybody. The base went from 60 to 80, and so the width of that rectangle is 80 minus 60, or 20 miles per hour. Now, looking back at the density histogram, if you were to look at the height of that rectangle, it would appear to be about 0.021. So when you compute the area of the rectangle, which is the base times the height, you're going to do a 20 times a 0.021, and if you were to pull out a calculator and try that, or do it in your head, you get about 0.42. That's the 42% who drove between 60 and 80 miles per hour. So that's how a density histogram works. You need to think about both the width and the rather strange looking height in order to get a proportion that fall within a certain range. We'll focus on density histograms the most, so let me make sure you know how to make them with R. You use the histogram function, and you can apply it in formula data input in the usual way, so a formula indicating the variable you're interested in, the variable fastest, and then indicating that the data in data frame in which you'll look to find that variable is Math 111 survey. And when you make a histogram, you need to make the x-axis very descriptive. You need to provide a good name for the variable, and you need to provide the units if at all possible. So those are miles per hour. So what you do is you put the title of the x-axis in quotes, and you feed it to this argument called xlab, or xlabel. You also want to provide a title for the histogram. That's done with the argument main, and so you put the desired title again in quotes. So there are 4 arguments to this function, all of them separated by the commas as you see here, and they produce an output that looks like this. You don't have to worry about the y-axis. That will say density. Now, histograms are very popular, but they can be a bit of a distraction. You focus very much on the individual rectangles, but what really is occurring in your mind when you look at how the rectangles go together is you might think of them as somehow following a curve in your mind's eye. So this is the same histogram for fastest, but I've drawn a curve that maybe the tops of those rectangles just seem to follow. This is called a density curve. In R, these are known as density plots, and you can make them using the density plot function. The syntax for the density plot function is exactly the same as the syntax for histogram, at least as far as the basic elements are concerned. There's a formula, and then after a comma, there's your data, and then an argument for the X label, and an argument for the title. Let's see what would happen if you were to apply just this code. You would get this output. So not the rectangles, but the shape they seem to follow. What R is trying to do here is indicate what the tops of rectangles of a histogram might look like if you were somehow able to look at the entire population instead of just this little sample of 71 students from the population. If you could somehow sample all of Georgetown College students and get their fastest speed and make a histogram, you could have lots of little tiny rectangles, and the tops of them might run through a curve that is estimated to look something like this one. Along the bottom, you see little blue dots, and those are the actual speeds that students drove. They form kind of a rug, and they're jittered a bit so that when 2 students drive the same speed, the points don't exactly overlay each other. And you can get a sense that where the density curve is high, the speeds are crowded together. And where the density curve is low, the speeds are quite spread apart. Here's that one person that drove 190 miles per hour and is creating this one little bump at the end. So in histograms and in density plots, heights go along with crowding. So let's pull back a bit and learn some general terminology for describing the shape of a distribution after you look at a histogram or a density plot. The basic terminology is this. You could say that the shape is symmetric if it looks like a mirror image of itself around some central vertical line. You could say it's skewed left if it looks like it has a tail going off to lower values of the variable. Skewed right if it looks like it has a tail going off to higher values. You could say it's unimodal if there appears to be only one major hump. Bimodal if there are two major humps. And I suppose it's possible to have more humps, but we don't particularly assign names to them. So this would be an example of a distribution whose shape we would describe as unimodal, because there's one hump here, and left skewed. Now, there are tiny little blips and blobbles along the way, but they're so tiny we're not going to consider them to be extra humps or extra modes. Those could be just little bits of chance variation that come in the collection of the data. This is just one hump. It's left skewed because there's a tail here going off towards lower values of whatever variable is under study. This would be unimodal and right skewed. This one we would consider right skewed, but also bimodal. This tail looks too important, this bump looks too important and too persistent to be just due to chance. So we'll say that there's two modes, two humps, and this is a bimodal distribution that's right skewed. We'll call this one unimodal, one hump. We don't pay attention to these little waggles here, just one hump. And we'll think of it also as roughly symmetric. If I were to draw a vertical line right about where my mouse is going, then the density curve looks the same on both sides of that vertical line, or approximately the same. So we've got a symmetric distribution. Unimodal and symmetric distributions are often called bell-shaped for obvious reasons. This is an example of a bimodal distribution. It's also a symmetric one because around this vertical line about here, the density plot appears to be mirror image of itself. This also would be an example of a bimodal and symmetric distribution. We've got humps at the ends and symmetry around this vertical line. Okay, still pulling back and getting ready for some other things. Let's think about an imaginary population. This occurs as a data frame inside the TigerStats package, and it's called ImagePop. So if you were to take a look at this data frame, some of the variables that you see, and this is just the first 6 people in the data frame here, some of the variables that you would see on them are their sex, they could be female or male, whether or not they were a math major, so these people were not, but there are some in the study later on, their income in dollars per year, so this person made $40,900, I guess. What do they think about capital punishment? Do they oppose the death penalty or do they favor it? And the first 6 people here opposed it, but there are some favors later on. And then just a fun one, how do you feel about the celebrity Kim Kardashian on a scale from 0 to 100, where 0 is you just despise her and 100 is you think she's the greatest thing ever? And so there's a range of ratings that are given here. This is called Kim Kardashian temperature, how warm or cold you are towards that particular celebrity. So let's focus on the numerical variable Kim Kardashian temp and describe it. So we'll get measures of center and spread, and we'll also look at some graphs so we can describe the shape. For measures of center and spread, we'll want to look at favstats. So favstats on Kim Kardashian, data is ImagePop, and out comes the favstats. And what shall we say about them? We'll talk about that in a little bit. For the graphical approach, We could try histograms, we could try density plots. How about some density plots? So density plot on the Kim Kardashian temp. Don't forget the little twiddles that indicates a formula here in your formula data input. I try to choose a nice name for the x-axis, point rating, and a decent title, Kim Kardashian temp. So what do we get here? It looks like a bimodal but symmetric distribution, and the center seems to be somewhere around 50, but in fact most of the values appear to be crowded near 0 or crowded near 100. So what do you do when you're describing a numerical distribution for just one variable? You want to describe the center, the spread, the shape. You should probably also mention any unusual features that the distribution has, such as an extremely large value, like in the fastest speeds, maybe the 190 miles per hour would be considered an outlier. Any sorts of unusual features or striking things about it. So, for center and spread, we might choose to use the mean and the standard deviation. And we might say that the mean is about 50.4. We got that off of favestats. With a standard deviation of 41.76. It's a rather large standard deviation, and it expresses the fact that so much of the data is way spread out from 50. It's clumped near 0 and near 100. Okay, how about the shape? Well, the distribution is symmetric, but it's bimodal with the modes near 0 and 100. So what might we say in summary? It seems that people either love her or hate her. Now our third graphical tool is the box plot. Let's start off with just a small imaginary data set. And so we've got just a few numbers here that have been stuck together in a list with the C function, and they range from about 7 to about 11. And we've stored them in an object we call imaginary data. So we'll make a box plot of imaginary data. Notice the formula input here. Since this variable is already present inside of our global environment simply by fact of having created this object, we don't need to provide some sort of data equals argument. R knows to look inside of its global environment to find imaginary data. We don't know what this is data of, so the X label will be very simple. We'll just call it X. And there's not too much to say about a title either, but let's practice providing one. As for the function itself, BWplot is short for box and whisker plot. So what do we get out? Well, we get a box, and we get whiskers going off to the sides, and we also get what are called hinges at the end. There's apparently a dot here inside the box. What's this all about? Well, the box plot, in theory, is an example of what we call the 5-number summary of a numerical variable, but put into graphical form. Now, the 5-number summary is the minimum value, and that'll be given at the lower hinge. That was 7.1 here. The next number in the 5-number summary is the first quartile. 25% of the values lie below it. So apparently the first quartile was maybe about an 8.2 or an 8.3. So the first whisker covers the lowest 25% of the values. Now the third number in the 5-number summary is the median of the data. And for this data, that was the number 9. So notice there's a dot right above 9. The end of the box is at the third quartile of the data, so that was some number just less than 10. So the middle half of the data is contained within this box. And then the upper 25% of the data are contained in the final whisker, and the maximum value of the data, the 11, are at the last hinge. So our 5 numbers in the 5-number summary are the minimum, first quartile, median, third quartile, and maximum. In theory, that's how it goes with the box plot. It displays the 5-number summary as a graph. It's a kind of combination numerical and graphical tool. But in practice, things will vary from this just a bit. So here we have a box plot of people's heights in the Math 111 survey data. And what we see is that there are two special dots off to the side. There were two people who were so short that they were considered outliers. Their height values were way below the other people in the study. Now, when R finds values that are possible outliers, it plots them on a box plot individually as their own points. And then the hinge that comes next to it is at the lowest level that would not be considered an outlier. It's still the case that the first whisker should contain about the lowest 25% of the data, and that the box should contain the middle 50%, and this dot here is still the median. There were no outliers in the upward direction. We can tell because there were no points plotted out here individually. So this hinge does represent the maximum height, which is about 78 inches, I believe, in the Math 111 survey data. So anyway, R will do the best job it can to locate possible outliers for you. You want to look at outliers in a data set because it's possible sometimes that they were data entry mistakes or should be removed from the data for one reason or another. Of course, sometimes they're just unusually large or unusually small values and should stay in the data when you're studying it. This graph is a little combination graph. It's like a density plot and a box plot put together. The density plot, though, has been made on the top here. Again, this is a density plot for fastest speed ever driven. But then a mirror image of the density plot has been pasted on underneath of it. And the combination of the two density plots plus everything in between, that's kind of this bisque color here, is called a violin plot for obvious reasons. I mean, it looks kind of like a violin or a cello laid on its side. Where the violin plot is thickest, that's where the data values are the most crowded together, and where it's thinner, the data values are spread out from each other. A box plot is done in combination with the violin plot, and here is the outlier at 190 miles per hour. And you can see that just like a density plot, a box plot can detect skewness. The way you tell the skewness is you look at the upper whisker, and this upper 25% seems to be more spread out than the lower whisker, the lowest 25%. When the upper whisker is significantly longer than the lower whisker, then you know that the data are skewed somewhat to the right. And similarly, you can detect left skewness as well when the lower whisker is a lot longer than the upper whisker. So box plots are very useful for that kind of thing, detecting skewness. They can be a little bit bad at detecting exactly where the crowding occurs. So for example, here is a combination violin and box plot for the Kim Kardashian temperature. And we see a very long box representing the middle 50% of the data. Nothing about that box itself tells us that there's almost no values around 40 to 60, and then instead most of the values are crowded around 0, around 100. Only the violin plot, with its density characteristic, indicates that crowding for us. So this is a good indication that no one graph necessarily is the only right way to display the distribution of a numerical variable, and these combination graphs are often a very good idea. If you want to learn how to make some combination graphs like this, you should consult the geek notes that go with Chapter 2 in our course notes. That's all for Part 2, so thank you for listening.